and welcome to the 101st video on our channel. My last video was about one big problem that used all the derivative rules we followed so far and was kind of a combination of everything. But this video is pretty much the exact opposite, almost a preparation for the next things. So, today I present to you what the two main pillars of derivative applications. So, there's a lot of derivative applications, and if you saw my intro to calculus video, you'll know that there are a lot of derivative applications, as I said earlier, and they're from many different fields, and they might really not seem related at all, but pretty much all of them use related rates and optimization in some sort, and there are many techniques to solve these two types of problems, but that will be covered in future videos. So let's move on to the pretty much the lesson. Derivatives is pretty much the universal language of change, and derivatives measure instantaneous rates of change, but can also be used to measure longer rates of change. So basically, there are two fundamental questions which drive most derivative applications. How fast is something changing related to another thing? So that's why it's called related rates. And then what's the best/worst case scenario is where optimization comes in. So if you ask yourself those two questions, how fast is something changing relative to another thing, and what's the best/worst case scenario, more often than not, you'll be able to figure it out using derivatives. So the main concept behind related rates is when multiple variables change simultaneously and are related by one equation. The focus is how the rate of change of one variable, let's say x, affects the other variables. Maybe y, maybe there's a third, even z. Or maybe it's the first variable is the amount of mangoes in a city, and the second variable is the population. I know these are just random, but it's just fun to say out these things. And maybe for homework, since there's not really any problems or anything, maybe a good idea would be to go and think about where you could apply related rates, or like situations where related rates could be useful besides the applications below, just in everyday life, and do the same for optimization. Now, the derivative reveals a lot of connections between changing quantities that wouldn't be possible without calculus, or would be very difficult to find without calculus. Now, the solving process is very simple. First, identify the relationships. Normally, it'll be given in a calculus problem. Then, differentiate with respect to time, most of the time, or another parameter. Then, solve for the unknown rate of change with some algebra. Now, it's really simple, but as I showed you in my last video, a few simple rules can turn into something very, very complicated. Now, why related rates matter everywhere? Now, real-world systems pretty much never involve isolated variables. There's always something affecting another in one way or another, even if it might not be obvious at first. Then the second one is change is always through interconnected systems. Because if you just have one object in a system or just one isolated system, it would only be a localized area of change and not a full spectrum of change. Then the third is understanding this is really crucial for prediction and control of many scenarios. Now, the core concept of optimization is a little different. Now, what it is using derivative to find maximum and minimum values. Then there's critical points where the derivative equals 0 or is undefined. There's the second derivative test, but really, we don't need to know these few things because this is just an overview of the applications and to explain the importance of related rates and optimization, since I won't really be doing any problems in this video. It's a pretty simple solving process for optimization. So define the objective function, what we want to optimize, either given in a problem or maybe we have to figure it out on our own. Then the second one is to identify constraints. Like, we can't have time be negative, or we can't have uh or we can't have something like food be negative, or any like physical quantity like that be negative, unless it's money and you're in debt, but we don't want that to happen. And then the third one is use calculus to find critical points, and the fourth is to verify and interpret results in the context of the problem. So that is about why optimization drives decision making. Now, every field seems to maximize benefits or minimize costs. I'm not sure about an exact field that would really not want to do that. Of course, you can put it in the comments if you have any idea, but I'm 99.99999% sure that that's probably not happened. There's no field like that. The second one is that optimization provides mathematical rigor to intuitive contexts like best or worst. But now we understand, yes, if we do this exact process with this derivative and this equation and everything, we'll start to understand how it works. Then the next is the final one is it transforms subjective better, like, oh, this performance is better than this performance, I like this interpretation more than this interpretation, into objective best, like this is the best since it had the more amount of correct notes played, etc. So that's pretty much how it works in pretty much life. Let's move on to some of the specific applications of optimization and related rates. So economics and business is where related rates is how changes in supply affect demand and price elasticity. Optimization is pretty simple and pretty intuitive, but the rigor of calculus will help a lot in actually figuring out this. Basically, maximizing profit, minimizing cost, finding optimal production levels as well to maximize profit and minimize cost, etc. Pretty much is the foundation of all derivative applications in economics and business. There's related rates for how stress in one component affects the entire structure, because when, let's say, you're building a building, it's not just going to be one structure, it's going to be many interconnected pipes, tubes, bars, everything, and so on. And optimization is designing systems for maximum maybe energy efficiency, minimum material usage, while also maybe having maximum durability from natural disasters like hurricanes and tornadoes. Now, biology and medicine also uses calculus, although I don't know many people like biology who are a big fan of math, but math is still very important in biology and medicine. Now, in related rates, it's how population changes except ecosystem balance, drug concentration changes, and the first one could be biology, but also maybe environmental science. The second one, optimization, is optimal dosing schedules and maximizing treatment effectiveness with least amount of doses, or maybe least costly the drug, or least maybe for a fact like least concentrated because that would cost more. Maybe you could dilute it, etc. But I don't know much about this. I'm only doing what I researched. For computer science applications, related rates is how algorithm performance scales with input size, and optimization is machine learning parameter tuning, like how many parameters should we have, what should all the parameters be, and network efficiency. Now we're here in environmental science and finance applications. For environmental science, related rates is temperature changes affect species migration, and optimization is resource allocation, or maybe the optimal amount of one species in one forest to have a more balanced ecosystem as a whole. And in finance, interest rate changes, how they affect portfolio values, and many other variables in the finance market, and optimization is pretty much risk return, maximum profit, least risk. Now, the biggest exception to this rule is physics and direct motion, but it still uses optimization. But normally, what you'll find in textbooks or more basic applications pretty much only use like the fundamental derivatives and not any of related rates and optimization. And that's pretty much summarizes the first point on this slide, where it often deals with direct relationships rather than optimizations or related systems. But related systems could be maybe systems of particle with conservation of momentum. But direct relationships, normally velocity and acceleration, are just fundamental derivatives of position. And direct motion normally focuses on describing motion itself, not caring to other changing quantities, assuming that everything is in an isolated system. Physics still uses our two pillars that we were discussing all this time, but not always as shown above. Related rates is how electric field changes affect magnetic fields, or how the collision of one particle to another affects both of their velocities or momentums. In optimization, the principle of least action in finding equilibrium states. Now, least action is something that's not normally taught in physics class, so I had to do my extra research and also look on YouTube in general. But there are pretty sure channels like Veritasium which cover the principle of least action. And the distinction is physics uses derivatives for direct description and related rates and like more related stuff to each other, but it's still a significant portion still uses not as much related rates and optimization, but just direct fundamental derivatives. Now, related rates reviews system behavior. It shows how complex systems respond to change. It enables prediction and control, and it's essential for understanding cause and effect in dynamic systems where things are changing and they're not always isolated or constant. And optimization drives progress, because every time we can optimize something, we find a better solution and we increase the thing that we want the most, whatever it may be. And mathematical optimization removes a ton of the guesswork, and it provides objective criteria instead of just opinion, which sometimes cannot be the best thing for if maybe a business, if it needs to flourish, or the amount of money they should spend in a certain supply. Both of them combined equals a better understanding. Now, let me show you a quick example, just objectively. So, if we have related rates where it's what happens when, and optimization, what's the best way to, what we can maybe do is we can plug in a lot for related rates and optimize it so that maybe that we can figure out a certain number of related rates, or optimize the relation between two quantities where maybe both of them is the most or both of them is the least, or one is the least or one is the most, etc., etc. Again, before we go, I want to talk about just how universally applicable they are. Nearly every field that uses derivative employs these concepts. They represent pretty much the fundamental ways us as humans think about change and improvement, and the same tools apply across vastly different domains, as I showed you here, from finance to environmental science. This is pretty much the power of mathematical abstraction, where we can understand these concepts, provides transferable problem-solving skills. As fields become more quantitative with the advance of technology, these applications become more and more crucial, and mathematical literacy in this area become increasingly valuable across all disciplines, because while computers might be able to run the calculations, if you understand how they work, we can create new applications and enable our society to flourish. Thank you so much for watching this video. I'm really happy that you watched this video all the way to the end, and if you found my content fun and educational, please make sure to like, subscribe, and hit that notification button for more awesome videos just like this, and please make sure to comment down below any questions, tips, or just anything for the channel that could be useful. I really appreciate it, and it helps a ton if you're there. So, thanks so much, see you in the next one, and bye-bye.